After defining integrals, we have also studied one important theorem, or rather lemma, which is known as Fatou's lemma, that deals with whether we can take the limit of the integral of a sequence of measurable functions with respect to mu, and how it is related to the integral of the limit of the sequence with respect to the same measure mu. Now, the question is there any use of this Fatou's lemma, or rather why it is so important in the context in the probability theory or the measure theory? Fortunately, the answer is yes, and we have a number of theorems. Actually, it can be seen that a number of theorems and results can be proved using this Fatou's lemma. Today, we will discuss two such important theorems. One is known as monotone convergence theorem, which deals with the functions which are monotonic, measurable functions that are monotonic, and also we will discuss another important theorem which is called dominated convergence theorem. So, these two theorems also play extremely important role in this probability theory, and they are used to evaluate many other results, theorems, and in many contexts they are used. So, I will also discuss one example in a diagrammatic fashion, so that it will be easy to understand what is the why or rather how this monotone convergence theorem really works in a real concrete example. So, we will do a little recap of the definition of an integral. Let f be a non-negative extended real valued measurable function on the measure space x script f and mu. Mu is the measure defined on capital X and script f. Then we define integration of f d mu equals to as supremo over phi of integral of phi d mu, such that where a phi is simple and phi is bounded above by f and phi is non-negative, that means 0 less than equals to phi less than equals to f. So, this is the definition of the integral of a non-negative extended real valued measurable function. And we also have learnt Fatou's lemma, which deals with the sequence of functions as well as the sequence of integrals of the sequence of functions. So, let f n be a sequence of non-negative measurable functions which converges almost everywhere on a set E that belongs to script f to a measurable function f. Now, note that both the sequence f n and f must be measurable. Then integration over E f d mu is less than equals to lim inf integration over E f n d mu, or we can write that just this lim inf is lying outside the integral sign. We can take this limit inside the integral sign, that means that is nothing but f. So, we can write this as integration limit n goes to infinity in lim inf of f n d mu less than equals to lim inf integration of f n d mu. So, this Fatou's lemma actually deals with the integration of the sequence of functions, rather the sequence maybe that gives actually the sequence of integrals with the integral of the limit of the sequence of functions, how they are related. So, as I have mentioned previously that this is one of the most important theorem or rather lemma in probability theory. So, we will demonstrate that how useful this lemma might be in order to prove two important theorems in probability theory. So, first we state what is known as monotone convergence theorem, or rather Lebesgue monotone convergence theorem, that is due to Lebesgue. So, again let us consider a sequence Fn which is an increasing sequence. Now, remember in Fatou's lemma we did not consider whether the sequence should be increasing or not, but in monotone convergence theorem this monotone terms itself suggests that there must be something monotonic in nature, and in this context we first consider a sequence Fn which is an increasing sequence non-negative of non-negative measurable functions which converges almost everywhere to a measurable function f. Now, remember if we drop this increasing part, then this is nothing but the condition of Fatou's lemma, but this increasing inclusion of this word increasing will lead us to development of another interesting theorem, and this theorem actually gives us exact equality in terms of the exact equality as far as the relations between limits are concerned. So, under these conditions we can prove that limit n goes to infinity, integration of f n d mu is exactly equals to integration of limit of f n, that is f d mu. And note that in Fatou's lemma we had inequality sign instead of equality sign, but there also we had some general non-negative measurable functions, there is no need to consider to be increasing, but in monotone convergence theorem it is emphasized that the sequence must be increasing in nature. Now, as we know that x, a random variable, is a measurable function, so we can consider the same analog for analogous to this theorem, another statement which is true for random variables. That is, if x n is a non-negative random variable that increases to x, then expectation of x n converges to expectation of x, that is L1 convergence. Let us now prove this theorem. The proof is nothing but application of Fatou's lemma, as I have already mentioned. So, this is very interesting. So, suppose since f n is non-negative and increasing, then we can immediately write 0 less than equals to f n less than equals to f for all n greater than equals to 1. Therefore, just by taking integration of f n d mu is less than equals to integral of f d mu. That follows from the simple definition of integration. Hence, by Fatou's lemma we can immediately write integration of f d mu. Remember, f is the limit of the sequence of function f n. By Fatou's lemma says that this should be less than equals to lim inf of integration of f n d mu. Now, we know that lim inf is always less than equals to lim sup. So, if again we can write less than equals to lim sup integration f n d mu, and this limit must be less than equals to integration f d mu, because it is increasing to f. So, that means what we have, that we started with integration f d mu which is less than equals to lim inf of the integral of sequence of functions with respect to mu, which is again less than equals to lim sup, that is trivially true, and this again less than equals to integration f d mu. So, this says that the limit exists and the limit is exactly equals to integration of f d mu, and hence the proof. Now, I will just demonstrate this monotone convergence theorem. So, monotone convergence theorem is just an application of Fatou's lemma and is very easy to prove. I will just demonstrate using a simple, very simple example and also diagrammatically. So, let us consider this example. F n x equals to e to the power x minus 1 by n, that increases to e to the power x, which is nothing but f x, and mu equals to x on 0 1, that means we consider a Lebesgue measure on the interval 0 1. Then let us calculate the left hand side of monotone convergence theorem, which is limit of n goes to infinity 0 to 1 f n d mu, that is limit n goes to infinity 0 to 1 e to the power x minus 1 by n dx, and if we calculate this integral, this is e to the power minus 1 by n into e minus 1, as n goes to infinity e to the power minus 1 by n goes to 1. So, the limit is exactly equals to e to the power 1, which is incidentally exactly equals to integration 0 to 1 e to the power x. Now, what is e to the power x? E to the power x is the limit of the sequence of functions, which in this case is e to the power x minus 1 by n, that is integration 0 to 1 f d mu. So, we see that this is a nice demonstration, although for a very simple functions, and we will see that we can apply this monotone convergence theorem. It has immense application in probability theory and in distribution theory. Now, let us demonstrate this diagrammatically. So, for n equals to 1, this red curve is giving us this f n x. Now, when we increase n equals to 3, this red curve shifted upward, that means it is increasing. So, naturally this green curve lies above on the red curve. This says that as n increases, the function is also increasing, and n equals to 50, we get a blue curve which is again lying above the green curve, that means again increasing in n. And another thing is that if we look at the black curve, that is nothing but the curve of limiting function, that is e to the power x, and this this blue curve and black curve almost they coincide almost fully as n gets larger. That means, if we increase n more and more, then obviously we will be able to distinguish between these two curves. Almost we will not be able to distinguish these two curves. That means, this curve converges as n goes to infinity. So, since this is an increasing function, increasing in n, and it converges, so we can apply monotone convergence theorem within a certain interval on which we can define a particular measure. And integral is nothing but integral can be interpreted as an area under the curve within a certain limits. So, if we draw the curve n equals to 1 and consider the integral under the curve f n x, that is e to the power x minus 1 by n, when integration is taken over 0 to 1 for n equals to 1, this gives us the red shaded area, and this gray shaded area is nothing but the area under the curve which is e to the power x between the value 0 1, which is the limiting curve. But it is clear that red is lying is much smaller, the red shaded area much smaller compared to the gray shaded area. Now, if we take n equals to 3, we see that the area of the red shaded area is increasing, and it is approaching towards the gray shaded area. So, it is almost covering most of the part of the gray shaded area, and what happens when n equals to 50, it is almost covering the entire gray shaded area. That means, the gray shaded area and the red shaded area have become almost equal. That means, the red shaded area, which is the integral of the sequence of functions, converges to the gray shaded area, which is the integral of the limit of the sequence of these functions. So, that this is a nice algebraic as well as geometric representation of monotone convergence theorem. Now, we will move on to consider another important theorem, which is called dominated convergence theorem. Here we assume that g is a function which is integrable over E, and f n be a sequence of measurable functions. Now, remember, here we are not considering that whether f n is increasing or not. We are just considering f n is f n to be a sequence of measurable functions, but there is one restriction on f n, such that f n x mod of that is less than equals to g x almost everywhere. That means, f n x is always bounded by g x almost everywhere on E, and f n x converges to f x almost everywhere on E. Then we get the more or less exactly the same type of result as we got in case of monotone convergence theorem, that is limit n goes to infinity integration over E f n d mu equals to integration over E f d mu. That means, we get exactly the same result, but under two different conditions. One, when we consider a sequence which is increasing sequence and increases to increasing sequence and converges to a function, and here in dominated convergence theorem we remove the increasing condition, the condition that the function should be increasing, but we imposed another restriction, that is modulus of f n x less than equals to g x almost everywhere. So, depending on the situation as we encounter later on, we can apply either monotone convergence theorem or dominated convergence theorem. Let us now give a sketch of the proof of this monotone convergence theorem, dominated convergence theorem. Let us define h n as g plus f n, and naturally this is greater than equals to 0, and h n is g minus f n, which is again greater than equals to 0, because g is always greater than equals to f n. Now, Fn and G must be non-negative obviously, and this is almost everywhere. Then by Fatou's lemma, so if we apply a Fatou's lemma on this Hn sequence of measurable functions, we can get integration G d mu plus integration f d mu, which is equals to integration of G plus f d mu. This first equality holds from the simple properties of some properties of this integration, which is less than equals to, now we apply Fatou's lemma, which is less than equals to lim inf of integration over E G plus Fn d mu. Again, if we split this by the application of the properties of integration, and G is not depending on n, so this first term is exactly equals to integration over E G d mu, and the second term is lim inf of integration E Fn d mu. So, let us call this 1, and similarly if we now we just note one important thing, that G is integrable. So, since G is integrable, so we can immediately write that G of d mu integration of that over E is less than infinity, and hence this will imply integration over E f d mu less than equal to infinity, because modulus of Fn is less than equals to G almost everywhere, and Fn increases, Fn actually converges to f. So, now we again apply Fatou's lemma to get on this function, which is G minus Fn, that is integration of G d mu minus integration E over E f d mu, which is equals to, by the simple properties of integral, integration G minus f d mu. Again applying Fatou's lemma, we get this thing less than equals to lim inf of integration over E G minus Fn. Again using the simple property, we can break this integral into two, which is first one is independent of n, that means there is no limit, that is integration of G d mu minus, since there is a minus and it is a lim inf. So, if I take the minus outside, this would be minus of lim sup integration over E Fn d mu. Thus, we have the two equations 1 and 2, and by 1 we immediately have integration over E f d mu is less than equals to lim inf integration Fn d mu, which is less than equals to integration G d mu, because Fn is always less than equals to G, and again the right hand side is independent of n. Then again applying similar logic on 2, we get integration f d mu is greater than equals to lim sup of integration Fn d mu. Now, by 3 and 4, we immediately have, if we start with the right hand side of 4, we can write lim sup of integration over E Fn d mu less than equals to integration, that is the left side of 4, less than equals to integration over E f d mu. Now, this integration over f d mu is again the left side of 3. So, this left side of 3 is less than equals to right side of 3, that is less than equals to lim inf integration over E Fn d mu. So, what we get is that lim sup of Fn d mu less than equals to integral f d mu less than equals to lim inf of integral Fn d mu, but we know that that is trivially, which is trivially true, that integration of lim inf of integration Fn d mu is less than equals to lim sup of integration Fn d mu. So, 3 and 4 suggests that integration of f d mu lies between lim sup of integration Fn d mu and lim inf of integration Fn d mu, and incidentally lim sup is less than equals to lim inf, but lim inf is less than equals to lim sup, that is always, that is trivially true, that is always true. So, by these two equations we get the proof, that means the proof is complete, because we get inequality on both sides, and hence we get the equality. So, we can say that since lim sup is less than equals to lim inf, we say the limit exists, and incidentally the limit, since the integration of f d mu lies between lim sup and lim inf, we can immediately say that limit of integral Fn d mu is equals to integration f d mu. So, that completes the proof of dominated convergence theorem. So, it is clear that dominated convergence theorem or monotone convergence theorem, these two theorems basically give us the same result, but under two different conditions. So, depending on the situations of our problems, we can apply either monotone convergence theorem or dominated convergence theorem. Now, a corollary to monotone convergence theorem is very interesting. So, let us suppose f n be a sequence of non-negative measurable functions, then we can get integration of summation n equals to 1 to infinity f n d mu equals to summation n equals to 1 to infinity integral f n d mu. That means, we can take this summation outside and inside the integral sign even though the equality will hold. And in case of random variables, we can immediately write expectation of summation equals to summation of expectation, although sum extends to infinity, n equals to 1 to infinity. And the proof is very easy. Let us start with a function g k which is summation n equals to 1 to k f n. Clearly, g k is increasing to summation n equals to 1 to infinity f n. So, since g k is an increasing function, we can immediately write using monotone convergence theorem that integration of this summation n equals to 1 to infinity f n, that is nothing but limit of g k equals to limit of k equals to infinity summation n equals to 1 to k integration f n d mu, and again if we take the limit, it is nothing but n equals to 1 to infinity integration f n d mu. So, this is a nice corollary, but it is of immense importance to show that expectation of sum equals to sum of expectation using monotone convergence theorem, even the sum extends over infinite number of variables, that means sequence of variables, provided some conditions are there. So, today we have proved two important theorems. One is monotone convergence theorem and another is dominated convergence theorem. We have used a general measure, that is mu. So, that means we are dealing with a sequence of measurable functions, and there are some conditions imposed on this sequence of measurable functions. So, for some assumptions or for some conditions, we have used monotone convergence theorem, and in reality if some other conditions are really seen, then we can use dominated convergence theorem. So, it depends on the situations in which we are working. The important thing that I would like to point out once again, that these theorems, rather the proofs of these theorems used the idea of Fatou's lemma, and also they have used heavily the concept of simple functions or the integration that is defined with respect to simple functions. So, as we have already discussed simple functions, in how we can define integrals with respect to simple functions. We have also proved Fatou's lemma. So, all these actually plays a significant role in proving many important theorems like monotone convergence theorem, dominated convergence theorem, and etc. in the area of probability theory and measure theory.